I have one more set operation to define. It's the complement of a set, and then we will do more with union, intersection, and difference. So to define this, well, we need the set A to sit inside some universal set U. So we need here U, which is our universe. And then we need, as I mentioned, A must be a subset of U. Then we define the complement of A. Well, the notation is like this with a line over it, and this is U minus A. So in words, this is everything in our universe besides the elements in A. It's everything not in A. Okay? Well, let's do an example. Here, A is the set 1, 2, 4, 8. B is the set 2, 6, 7. And U, our universe, is all natural numbers less than or equal to 8. If you want to, maybe I will, we can write out U. This is just 1, 2, 3, 4, 5, 6, 7, and 8. Okay? And certainly, just as a comment, you notice that both A and B sit inside the universe U. So now we have these 8 different sets we will calculate. Okay? We start off with 2 complements, the complement of A and the complement of B. So this is everything that is not in A, which would be 3, 5, 6, and 7. Okay? B complement, well, this is everything that's not in B. So we have 1, 3, 4, 5, and 8. Okay? Now, once we have these 2 and these 2, we can compute the other 6 using the operations that we've been thinking about: intersection, union, and set difference. So here, this is A intersect B complement. We look at this, and what elements are in common? Well, I see 1 and 8 and 4. Okay, 1, 4, 8, 1, 4, 8. A union B. Well, we don't have any complements in this example. We just take everything in A, everything in B, and make it in one big set. So this is 1, 2, 4, 8, and 6, and 7. Okay? Now, B minus A complement. We start off looking here, and then we remove the elements that are in A complement, which is here. So what will I remove? I will remove 6 and 7, and I'm left with just this singleton with the element 2. Now, B intersect B complement. Here's B complement, here's B, and do they share any elements? Well, no. We see 1, 2, 3, 4, 5, 6, 7, 8. Empty set. And this makes sense, right? Because if you think about the definition, B complement contains the elements not in B. So it makes sense that this is empty. Now we have 2 more. A complement intersect B complement. So what's common to both of these? I see 3 and 5. And the last one, we look here at the union, which also sits inside the universe U, and we take the complement. Well, what's missing? We have 1, 2, I need 3. 3 is not in the union, and then 4, 5. And then 6, 7, 8. Okay, this will be a union B, then we take a complement. Now I want to make some observations here. So this is a great activity that we have done to practice union, intersection, complement, set difference. But I want to make some more observations. As I said, the first thing that you'll notice for this example, You see, these two are equal. So I'll make that observation here in this example. And this is all that I'm saying at the moment. We see A complement intersect B complement is A union B complement. But there's really more that I can say for some of these, or that I want to say for some of these. For example, let's look at this one here. A intersect B complement, okay? Perhaps I will erase this A union B because I don't have anything more to say about that one right now. But let's look here. Is there another way we can write this same set? Well, the answer is yes. This 1, 8, and 4. If you notice, this is start with A, now remove B. I would remove 2. So I can also write this as A minus B, this one. And again, for this example is all I'm saying at the moment. Now another thing that I want to observe is here. This B minus A complement, this is how we calculated it, but in this example, if we just intersect A and B, what's common to both? Well, we get the same thing. It's exactly 2. So this is also A intersect B. Okay, so what we see just by looking at this example, we see a few of these that you could write more than one way, or at least that I've written more than one way. And so what we want to discuss now is a way we can visualize sets, set operations, and visualize the set equality in a diagram. And it's something called a Venn diagram. This is what we will discuss now. I rewrote these 3 that we realized, or that we at least witnessed in our example. I rewrote them because I want to come back to that after I define a Venn diagram. But as I mentioned, we can visualize sets and set operations using a Venn diagram. So what is a Venn diagram? Well, I'll draw first a Venn diagram for just one set sitting inside a universe. We will typically draw a box. And this is our universe U, or a rectangle. And then sitting inside U is a set A. And you really think about the set abstractly as just occupying the space that occupies this circle, okay? So this is A sitting inside a universe. And we will use shading to illustrate set operations. For example, in this Venn diagram, I can illustrate a complement by shading. That would be everything not in A. So a complement is all of this out here. This is the Venn diagram. Let me show you what a Venn diagram for 2 sets looks like. You have your universe U, and then you want to draw 2 sets, A and B, sort of in the abstract sense. An A and a B look like this. And as I mentioned, just like here, you think about this set occupying the space inside the circle. So everything in here is set A, everything in here is set B. And so for example, I will in this Venn diagram illustrate the set A intersect B. This would be what's common to both. And I can shade this. It would be this region here. This is a Venn diagram for A intersect B. And we can do more. In fact, I will do the operations we have discussed. Well, let's see the Venn diagrams for these other set operations. Then I will return to these 3 purple equations. For A minus B, well, you start with everything in A. That would be all of this circle, but then you remove what's in B. So what we're left with is just here, the elements that are in A and not in B. Similarly, if we want a Venn diagram for B minus A, we would take all of B and then remove what's in A. So we would just be left with this part here. All of this is B minus A. The final one here is the union. Well, you want everything in A or everything in B. And of course, you could be in both A and B. So this would just be all of this here. Everything inside colored in. This will be A union B. These are very pretty. We have lots of pretty colored markers, fortunately, to use for these Venn diagrams. Now, what I'm going to do is I will have 6 Venn diagrams, and we should be able to realize the equality of all of these. Now, just as a comment, before I draw the Venn diagrams, we will, later in the semester, be proving things like this, like this, like this, in what's called a set theoretic proof. And this picture is not a set theoretic proof, but for now it gives us this beautiful way to visualize sets, see set operations, and really get straight in our mind what's going on with some of these. Okay, so let's do these now. Now I am ready to begin, but let me point out a mistake that I had on the board. I had this equation written a second time here instead of this one, which was the third one that we saw in our example. Okay, so what we are doing now is each one of these, I will just say it holds in general. We witnessed it in our example, but I will draw Venn diagrams. Over here is the left-hand side of the equations. Over here is the right-hand side of the equations. And we should see when we shade things in that the regions that are shaded here and here match up. The regions that are shaded here and here match up. And then here and here match up like this. Okay, so here we go. I will start over here on this side because I think this side takes fewer steps. This is just a set difference. This is an intersection, and then this is a complement of a union. So these two, in fact, we've already had on the board. So let's begin on this side. A minus B. A intersect B is everything common to both A and B. Now, this one I will think a little bit. We take the union, which would be everything inside of what I'm outlining. Okay, let's make this box smaller so I don't have as much to color in here, and then I'll put U. Everything inside of this turquoise color is the union, but I want to take the complement. So that would say out here, this is A union B complement. Okay, now let's work with these left-hand sides. Let's start with this one. I will do an intermediate step where I shade in B complement. So this is everything that is not in B, but I will just put these sort of green lines coming out to illustrate where B complement is. This is an intermediate step. Okay, this is B complement, but now you see I want to intersect this with A, and here's where I will shade in. So I take A intersected with what's lined in light green, and we get exactly this. So my final answer is what is colored in solid purple. Okay, and you notice that it's the exact same region that I have over here, which would illustrate at least this one generally, not just for our example. Now let's move to here, B minus A complement. So just as I did here, I will have this intermediate step where I will put green lines on A complement. Okay, this is A complement. Now I want B, start with B and remove what is lined in green. That's A complement. And what we're left with is exactly this. What's shaded in purple here matches what's shaded in blue here. And this illustrates, that's this one, this equality using this Venn diagram approach. The final one, we want A complement intersect B complement. So I will do two sets of lines. A complement is in green. Okay. B complement perhaps in orange. Now it's an intersection. So when I look at this, what I want to do is find where I see both green and orange lines. This would be the intersection operation, and then I will shade this in purple. And you notice it is all outside here because this is just orange, this is just green, this part has no shading, and so what we get is all out here. Okay? It looks so good because, again, we have this one. This relationship or this set equality is illustrated in the fact that these diagrams, the shading is exactly the same. Okay? Now, there's no reason to only work with two sets in a Venn diagram. In fact, we can say a lot with a Venn diagram on three sets. So let's do some of these now. Well, I have switched to my iPad for Venn diagrams with three sets. But you see here, and maybe in these top two, I need to label my universe, U. This is how we draw a Venn diagram for three sets. We have the set A, we have the set B, the set C, and you want to draw them abstract so that you have all possible intersections appearing. For example, before I look here, this here you see this part is A intersect C, for instance, and then here would be A intersect B is this region in red, and we can have all kinds of combinations involving the three sets A, B, and C using a Venn diagram like this. So what we will do is we will shade these four examples. The first is A intersect B intersect C, and in this here we don't need parentheses because, for instance, if we did these two first we take the intersection of A and B, and then you intersect with C. It's the same thing as if you do this. And either one of those, which is the intersection of all three, just gives you everything common to A, B, and C. And that is here. Okay. So this is this green region. Now, maybe we'll do this one over here. Next, we want A intersect B, and then union A intersect C. So maybe I will do these in two different colors. A intersect B is this part. And then we want to union A intersect C, which is here. And this, everything that is shaded is the region. So it's these two pieces, the green and the blue together give us A intersect B, union A intersect C. Very nice. Now let's move on to this one. We start with B minus C. So we take everything in B, we remove what's in C, and what we're left with will be, okay, but then union A. So I'm adding to this picture all of A. And this region is, or what's shaded, both the blue and the green together is B minus C union A. Okay, we have one more on this page. We want, now this is an intersection, so I'm going to first draw lines kind of like I did on the board when we only had two sets. So first I want A union B. This is A union B, at least in lines, and then I will shade once I have my final answer. Then I want to intersect with C complement This is everything not in C. So let's put vertical lines for everything not in C. Now we can see very clearly the overlap. We want the yellow and the, I guess it's a light orange, and this will be the intersection. We are intersecting. My final answer is shaded in blue. Okay, that is A, union B, intersect C, complement. Okay, so here are 4 examples where we shaded the regions corresponding to different sets when we had 3 sets in a Venn diagram. Now I have one more question, and we want to find an expression for what's shaded. So now it's a different question, right? I'm starting with something shaded and asking you, what is this? You see, there are multiple options here. One thing I see, so one option is we can start with B and then subtract the union of A and C, right? Because that would say, start here, this would be all of B, and then we remove the things that are in A or are in C, the union. And this would be removing this and removing this, and we'd be left precisely with this green region. But this isn't the only answer. So another answer, well, again, I want to start with B, and then let's say I take away A. Now what do I have? I'm going to see if I can make it out of something like this. Start with B, that would be here. If I remove what's in A, now I have this. Okay, it's not right yet, but then I could then take this set and then minus C, and I will be left precisely with what we see in this picture. So I want to take this set and minus C. So this is another answer for the exact same green region. And just as a comment, in this one, unlike when I had the intersection of all 3, here I absolutely need parentheses. So you might think, what would happen if you put the parentheses there instead? And I will just tell you, it's a different set. So that would be a nice exercise for you to think about. These parentheses here are quite important. I will end today's lesson with a question which we can think about using Venn diagrams, but also this is something we'll touch on more than one time this semester, so it's a nice way to end our discussion. Well, the question is as follows. Say you have finite sets A and B. Then is the cardinality of A union B equal the cardinality of A plus cardinality of B? Okay. You might know the answer already just by thinking about some examples we've done. But if we think in terms of Venn diagrams, which is how I would think about this question, we think of A occupying this circle, B occupying this circle, and if we think about just adding, now we have finite sets, add everything in here, add everything in here. We're going to be counting this stuff in the intersection 2 times, and that's going to be more than this union. So the answer, generally, no. That is not true. Now there is a case when it holds. Let me show you though what the Venn diagram looks like. It would be like this. So when sets A and B are disjoint, which this is what we see in this picture, then it's wonderful. You can just add cardinality of A, cardinality of B, cardinality of A, add them, you get the cardinality of the union. And just as a comment, what does disjoint mean? We see it in the picture, but disjoint, this means that A intersect B is empty. This means Okay? Now, let's take a few moments and think about what is true in general, which this goes back to this Venn diagram for finite sets A and B. And I was starting to talk about it, is why just adding the two doesn't work. Okay, here, add up everything in A. Now, I will shade, okay? If you notice, I've already counted everything in A intersect B because I counted it in A. Now, add up everything in B. So now, I've counted what's in the intersection 2 times, which is too much because I only want everything in the intersection to appear 1 time in the union, cardinality of the union. So I must subtract. Okay, so the general and correct statement is cardinality of A plus cardinality of B minus. But generally, this is not true. This is the correct equation. Generally, and even when you have disjoint sets, this is 0, cardinality of the empty set, and so this would hold also for that. So this is really the relationship here between the cardinality of the union, cardinality of A, and cardinality of B when you have finite sets.